In this video, we will go over inferencing, which is a very important part of just very, very crucial and essential part of regression analysis, hypothesis testing. But yeah, inferencing and hypothesis testing, that's what we're going to go over today. Obviously, there will be more hypothesis tests that I will cover in the future, but in this video, I'm finally covering the hypothesis testing in more specific detail compared to the chi-squared or the t statistic I mentioned way back in my last set of videos. Yeah, but without being said, let's start. So basically, inferencing is a kind of a general word. It's when we hypothesis test because we want to ask ourselves how confident we are about an assumption. So when we find that the expected value of a random variable, let's say for a dice roll going all the way back, is like 3.5, we're not completely confident. We know, well, I guess in this case, we know that the dice won't land in the value of 3.5 because obviously it has to be a whole number, but nevertheless, my point stands is that the random variable won't always land in the exact mean value. And so what we usually do is, with the help of what we call the interval estimator, we create a confidence interval, which you can see here. So B2 minus C and plus C. C representing the value of the range, what B2 can range from. And so if we recall that the B2 coefficient in our regression has a normal distribution of beta 2, the so-called true parameter that we can't actually calculate, and it has a variance of B2, again a different formula from just the variance of a random variable. Then we can also obtain a standardized normal random variable. So this formula right here, it should look familiar. It was, if you, when we normalized, we did like the mean minus the or the value minus the mu divided by the standard deviation. And in this case, we're pretty much doing the same thing. We're subtracting our like fitted B2 minus the true parameter divided by the standard error. And in a lot of cases, I know the standard error is based on the standard deviation divided by the square root of n, but we kind of assume the standard error is already, like, we kind of assume they're pretty, it's the same thing to a standard deviation, because we have to account for the sample size by default. And again, this is like a notation for the probability of like our random variable of B2 in this case, landing from the given confidence interval, and then let's say we're trying to find a 95% probability of it. So this will be our like full formal notation. But when you solve for it, you don't actually write for this. All right, so if you want to create a confidence interval for the normal standardized distribution for 95%, the z-score the z-score is 1.96. So B2 plus or minus 1.96, and then the standard error of B2. However, because we're dealing with a sample size, we have to use the t-distribution, because the normal distribution, that's when our sample size, we don't account for it. But if we do have a sample size, we'll use the standard error, because the sample size matters a lot when we're fitting our B2 value and all that. And recall this formula that actually, I'm not sure if I've given this in my previous lecture, but this is the formula for the standard error of B2. It should look similar because I did mention variance, I know that. And then T statistic is basically the same, except it's based off the degrees of freedom because we have we have B1 and B2. But other than that, it's the same as the Z statistic. And so if we can kind of look at it visually. Actually, okay, so let's look at what the critical value is trying to measure. It's simply put, it's so when we're trying to find a critical value, we'll always eventually look at either we'll find it by software or we'll look at the t-distribution table. But it's based off our confidence interval, so which is represented by alpha, and then m, or alpha, and then we'll divide it by 2 if it's a two-tailed test, and then 1 minus because we're trying to find we're trying to kind of overpass or bypass the critical value. We're trying to reject the main region, and then m is the degrees of freedom. And so the critical value is important for creating confidence intervals and hypothesis testing. Now, I don't think I've done a very good job of explaining what the critical value is calculated, so or what it's actually used for, I guess, so far. So we can do an example here. And so if let's say for our typical income and food expenditure equation, we're given that the sample size is 42, and we want to create a 95% confidence interval for B2 or beta 2. And then our standard error is usually given below the equation. So for our beta 2 it's 2, and for our beta 1 it's 30. And so if you want to create a confidence interval, our critical value, TC for short, just a second, I don't know why I can't get this to work. All right, there we go. Oops. Okay, so TC for short, we can notate that as 1 minus alpha based on the critical values. So we'll use alpha equals 0.05. And then degrees of freedom, which is 42 minus 2, so 40. And so again, this isn't necessarily a formula. This is what we're accounting for to find a critical value. So if you want to do this by hand, you'll have to use the t-distribution table. And if you do that, we get around a value of 2. And so in order to create the confidence interval, we want to use a formula that we were given over here, or yeah, over here. So the plus or minus B2 plus or minus C, which is given by the critical value times the standard error of B2. So we know that the beta 2, the mean for the beta 2 is 10. That's what we estimated by default. We didn't actually calculate that, but that's what we're assuming. So we'll say 10 plus or minus the critical value, which in this case is 2, and then the standard error of B2, which we were given that it's 2. And so if we do 2 times 2, which is 4, and then 10 minus 4, which is 6, our minimum value will be 6, and then our higher value will be 14. And so our interpretation is actually what's more important. So how do what does this mean? Well, it's we have to be very specific with this because the word of our analysis gets a little tricky, but we basically say the interval estimator, which is a key part of our interpretation, that based on the interval estimator, that then beta 2 belongs within 6 to 14 with the 95% probability. Now, even if you don't say exactly what I just said, it should be fine. But it doesn't necessarily mean that the 95% we're 95% sure that a random variable will fall in these two values. It's not as simple as that. I think again it gets a little wordy, but I think when we have to mention beta 2 and like the relationship of the true parameter and then b2 and then how b2 has a 95% chance of belonging to this interval, or beta 2 has a 95% chance of belonging to this interval based on the interval estimator. I'm sorry for the kind of further confusion. It is a little difficult to interpret. Obviously, you can ChatGPT or whatever, but you get the idea. Just a general gist. Yeah. All right. So let's move on from confidence intervals. Let's say we want to ask like how income specifically affects food expenditure. We don't, or does income affect food expenditure? So we're not creating a confidence interval, although we can do that later for this question. Essentially what we're asking is beta 2 or b2 far enough from 0 so that we can conclude that it actually does affect food expenditure, right? So what I'm gonna do is I'm gonna introduce two set of hypotheses called the null hypothesis and the alternative hypothesis. And essentially what the null hypothesis is saying is that the coefficient of B2 has no effect in our food expenditure. And our alternative saying is what we're like challenging the null against. It's saying it actually does have an effect against food expenditure. And so in general cases, the null and alternative hypothesis, it's not just for does like X affect Y. We use this for like every type of hypothesis testing. And so just a general way of thinking what the null hypothesis will be compared to the alternative is kind of think of the null as saying like, oh, we don't need to fix anything. It's okay. Like it's good as it is. Oftentimes it's gonna kind of like lean towards that sort. And then the alternative is like, oh no, we need to like make a change, or it's like it feels like it's challenging the null hypothesis. Yeah, just a useful tip in my opinion. All right, and so the way we mathematically figure this out is we will use what we call the test statistic. So what we calculated here, not the z statistic, but the t statistic. And so if I do TS, which is what I write for the test statistic in short, if the absolute value of it is greater than the critical value, then we can reject the hypothesis saying that hypothesis which says the beta 2 has no effect on income, or that income has no effect on food expenditure, excuse me. And the reason why we use absolute value can be seen visually here. If we, because we're using a two-tailed test, whether income has a greater effect or negative effect, positive or negative effect on food expenditure doesn't necessarily matter in this case. We all we want to see is if B2 is large enough. Okay, so let's see here. Okay, so let's let's calculate the t-statistic. So if we use this formula over here, that's 10 minus B2. Now, our formula here for the test statistics always going to be based on the null. So it's saying it's 0. And so our beta 2, or C, what we usually call, will be at 0. And then our standard error was given 2. And so our test statistic is 5. And we already calculated the critical value based on the t distribution, which we found out to be around 2. And so because, just insert some space, because the absolute value of absolute 5 is greater than 2, or the t-statistic is greater than the critical value, we can reject the null hypothesis saying that income has no effect on food expenditure. And intuitively it would make sense because our whole point of analyzing these two variables is that income likely has an effect on food expenditure. Okay, and like I said, remember we're just testing if income has a positive effect, or if income has any effect, not a positive effect. But if we wanted to test if income has a positive effect, then instead of saying does not equal to 0, we would say greater than 0 as our alternative hypothesis. And then we also have to count, because we're doing that, we also have to count for, like, we can't divide by 2 anymore from the alpha, because we're using a one-tailed test, not a two-tailed test. So even if our alpha lands here, or critical value lands here, we have to accept the null hypothesis because we're only concerned with beta 2 being greater than 0. And we're not using the absolute value of the t-statistic either to compare the critical value. We just have to compare the actual value. But in our example, we did get a positive value of 5, so we would still reject a null in this case. But if we got like a negative 5, then we would not be able to reject and accept the null. And then finally, just this isn't the most common. We don't occasionally like say these type 1, type 2 errors in common, just like casual terms. I've never heard like a professor say it in my experience, but just good to know down the road. A type 1 error is when we reject a null when we should accept it. So like, let's say instead of a 5 here, we got a 1 somehow, or that's not a good example. That's a type 2 error, but let's say like reject a null when we should accept. So let's say we got let's say the actual answer of our test statistic here is like a 1, but we got a 5. Our correct answer should be to accept the null, but we reject it instead. So that's a mistake. And then type 2 is the other way around, where the actual value of it is a 5, but we got a 1. Then since 1 is less than 2, we would accept the null, right? We would reject the alternative. But again, that's what we call a type 2 error. All right. In the next video, I'll go over more inferencing. So p-values, which is actually a more efficient way of knowing if we should reject the null or not. And then I'll also go into like linear combination of our regression analysis.